This is Ratish Jayabharati. We are now in session 5A, test and verification. We have 4 papers in this particular session. The first one will be on OpenCGRE, and the second one will be on perf DPT. And then we have 2 more. We will introduce you to those as we go. The first presenter is going to be Dr. Cheng Tang. Cheng Tang is a postdoc from Pacific Northwest National Laboratories. His research interests are about computer architecture, machine learning accelerators, and network on a chip, etc. And he will be presenting the paper OpenCGRE, an open source framework for modeling, testing, and evaluating CGREs.
Functionality of a target design. And it could also. All right. Hi, everyone. I'm Cheng Tan from PNNL. I'm now giving the presentation about our proposed framework, OpenCGRE, an open source unified framework for modeling, testing, and evaluating CGREs. So a CGRE framework should contain 3 main parts: modeling, testing, and evaluating. For modeling, functional level modeling provides the fastest way to emulate the functionality of a target design. And it could also be used as the golden model for verification. Many existing CGRE compilers include cycle level modeling with cycle accuracy. The registry transfer level, also known as the RTL, right, modeling, is more and more important currently with the open source community growing. It provides the most accurate model and provides synthesizable Verilog to the users. For testing, a robust framework should be able to perform unit testing and integration testing conveniently. OpenCGRE also enables the property-based random testing to speed up the verification procedure. So to perform the evaluation, a CGRE framework should be able to simulate a design, generate corresponding synthesizable Verilog, and perform the area, power, and timing characterization. However, not all these features are exploited by existing frameworks. In contrast, OpenCGRE incorporates all these features into a unified Python-based framework to facilitate the design space exploration of CGRE. Okay, so this figure shows the overview of OpenCGRE, and I will talk about these 3 components one by one in this presentation. So OpenCGRE provides a modular architecture design for all kinds of CGREs. All the basic modules are implemented in a highly parameterizable way. For example, a user can parameterize the functional unit type, the size of control and data memory, the number of registers, and even the network topologies. So all the modules are designed with standard send-receive interfaces, so the user can easily plug in their own design by following the same interface standard. A functional unit could either be basic or complex. A basic functional unit means just like an adder, a shifter, or an ALU. In contrast, a complex functional unit in OpenCGRE is composed of multiple basic functional units, such as a multiplier followed by an adder to form a MAC unit, which can perform multiplication with addition in a single cycle, right? So all the models and different abstract levels are implemented in Python. So a functional level model just executes every node in the data flow graph one by one until the final branch operation is valid and reached. On the other hand, the cycle level and registry transfer level modeling should provide more detailed structural and behavioral information. So in this way, the synthesizable Verilog can be generated finally. So to make a CGRE work efficiently, compiler support is also essential. OpenCGRE provides a heuristic algorithm to enable DFG mapping onto the CGRE. So the CGRE is represented as modular routing resource graph. The novelty here is that our algorithm takes the complex functional unit into consideration. So if there is a complex functional unit in the CGRE design, the corresponding operation pattern supported by the function unit found in the DFG has the higher priority to be mapped onto that functional unit. So the other operations, probably the basic simple operation like the addition and multiplication, right? They could be mapped onto the other basic functional units. For testing, OpenCGRE extensively applied the unit testing and integration testing. As the figure shows, users need to specify the expected output for each input set. Moreover, property-based random testing is achieved by leveraging the open-source Python-based hypothesis framework, which helps you to automatically and randomly shrink your design until the bug is found in a minimum design complexity. This can significantly save the engineering effort in debugging. And shown in the code, we can see that the hypothesis can automatically locate or find the minimum combination of the functionalities that cause the bug. So the last part is about the evaluation. We use a set of representative embedded applications to drive the evaluation in this work. Firstly, both the compiler and the cycle-level models can provide the throughput information across all the target application kernels. OpenCGRE can also leverage a bunch of EDA scripts to drive the characterization about the power area and timing. So by doing this, users can get an initial idea about whether the performance is as expected or it exceeds your power or area budget in the design space exploration. We also illustrate a systematic way to design a heterogeneous CGRE. To be specific, we first extract the longest recurrence cycle in the DFG, and then we can design complex functional unit to execute the most common operation chains in single cycle. So this table shows what are the most common operation chains extracted from the representative application kernels. Afterwards, certain tiles of a homogeneous CGRE can be equipped with the complex functional unit to form a heterogeneous one. However, parameterizing functionalities is not an easy work in existing frameworks. Normally, the frameworks are able to allow users to parameterize the number of ports, registers, tails, but not the functionality. Fortunately, OpenCGRE's parameterization system can help you to do this kind of parameterization before the module elaboration. So the code shows only a few lines of Python code can help you to specify the functionalities of specific tiles to form a heterogeneous CGRE. So, and finally, OpenCGRE can generate the corresponding synthesizable Verilog of your target CGRE design. So here comes the conclusion. OpenCGRE enables the multi-level modeling to facilitate the CGRE design space exploration. It provides extensive test harnesses to test CGRE modeled at different abstract levels. And it can also simulate CGREs at different levels and generate the corresponding synthesizable Verilog and drive different CAD2 flows to obtain the CGRE power area timing statistics. So besides these takeaways, OpenCGRE is open source and available in GitHub, and welcome to check it out. That ends my talk. Thanks.
Thank you, Dr. Tan. Can I open for questions? Are there any questions from the audience? Okay, I don't see anything specifically. So maybe I'll start off with the one. Can you kind of describe some of the accelerators that can be easily modeled by your framework?
Yeah, so our OpenCGRE framework is very parameterizable, right? So you can actually specify the functionality of each tile. So it's very convenient for a user to model a systolic array or a Marie accelerator or some kind of machine learning accelerator based on your requirements. Yeah, you just need to specify the functionality, then identify the topology, then the accelerator will come up. Yeah.
Okay. Maybe a quick one is there a reason you chose Python for using
Yeah.
for your
So
infrastructure?
for the framework, like some people like the popular one maybe also like the Chisel, right? Chisel use the Scala, and we use the fundamental framework like Pymetal. So the Python is chosen because of its convenience. So it's kind of the open source hardware community like want to make this kind of tools to open to all levels of users, to the application level user or the hardware users, to make it easier to be used. So the Python is chosen. And also Python is very convenient for people to verify your design. Like in Python, you can write your own test bench very easy, right? On the other hand, if you write in the Verilog, then it is disaster, right? So Python is chosen in like these two reasons. One is for the different level users, and the other is very easy for testing.
Okay. Again, thank you, Dr. Tan. We will move on to the next paper. This paper is titled PerfDPT, Efficient Performance Regression Testing of Dynamic Binary Translation. The presenter is going to be Jin Wu, who is a PhD student at the Harbin Institute of Technology in China. He's also a joint student at the University of Georgia as well. So let me start.
Hello everyone. Today I'll be introducing our recent research work, PerfDPT, Efficient Performance Regression Testing of Dynamic Binary Translation. I'm Jin Wu. This project is supported by Harbin Institute of Technology and the University of Georgia. DBT is a key enabling technology. It dynamically translates binary code from a guest ISA to a host ISA. However, the code base of DBT suffers from frequent changes. As shown in this figure, QEMU has more than 10 commits on average every day. In this case, its performance may change frequently across different versions. Thus, it is necessary to conduct regression testing before each commit. However, current testing suites usually take an extremely long time, which are not suitable for quick and frequent tests. For example, it takes 8 hours for QEMU to complete the integer benchmarks of Spec CPU 2017 with reference input. Although there are smaller input datasets, such as test, it cannot reflect the same performance changes as the reference dataset. As shown in these two figures, the test and reference input have quite different performance results across different QEMU versions. So, the problem here is how we can achieve efficient performance regression testing of a DBT system. Our observation shows that a smaller test suite can be generated from existing benchmarks by scaling down the hottest translation units. The generated test program can have the similar behavior and performance results compared to the original long-running benchmarks. Based on this idea, we developed PerfDPT, which can automatically generate test programs to test DBT systems. It takes the binary of the original test suite as input. The profiler collects runtime hotness data of each executed translation unit. Then, the units are passed to the analyzer, which scans each instruction and analyzes memory consumption. Both hotness and memory consumption information are then fed to the program generator for memory access preparation and setting up iteration factors for each unit. And then the inline assembly is generated based on the input. Note that we must modify some instructions to make the program runnable. Finally, the source code is compiled as the test program we generated. Now, let's see an example test program generated by ProfDBT. According to the previous analysis, memory objects consumed by the testing units are declared first, and then the space for each object is located and initialized. The major part of this program is the test function. Extracted guest assembly is placed here, and the execution times is controlled by iteration and scaling factors. In the end, the occupied memory is cleaned up. Please refer to our paper for more details. We are curious about the testing efficiency and effectiveness of the programs generated by ProfDBT. Now let's see some results. We evaluated the testing time based on spec 2017 on 10 QEMU releases, with the reference dataset as input. Execution time of both the original benchmarks and the test programs generated by ProfDBT are measured for comparison. The average speedup of all the QEMU versions for each benchmark is shown in the figure. Our test programs run up to 150 times faster, with an average of 70 times. Note that the iteration times is adjustable. There is a trade-off between testing time and the accuracy. With this setup, our approach can also reflect similar performance trends to the result of original spec benchmarks. The next experiment shows the effectiveness of ProfDBT. We compared the execution time of original spec benchmarks and ProfDBT generated ones. The y-axis represents the normalized execution time. The curves of ProfDBT are close to those of original spec, which is quite different from the figures we saw in the previous slide using test dataset for testing QEMU. As a result, ProfDBT is able to reflect real performance changes, which is similar to the result of reference datasets, while the testing time is shortened from over 8 hours to a few minutes. This is my presentation, and I'd be more than happy to take questions. Thank you.
Okay, now that I'm unmuted, thank you, Jin. Let's see if there are any questions, and I don't see anything from the audience. Anybody with questions? But let me warm you up a little bit. If you were talking about the performance of PerfDBT, can you also apply it for evaluating the correctness?
This is a very good question. This question is about evaluating the correctness. Actually, current implementation of PerfDBT can only evaluate the performance, but this approach does support evaluating the correctness. We can simply add input and output check before and after a translation block, or even a set of input and output data for a single translation block to verify the correctness. So the answer is yes, it is possible to evaluate the correctness with PerfDBT, although it requires some additional work. Thank you.
Okay. Maybe one more. What are the instruction set architectures that you support through your methodology?
Now we demonstrate PerfDBT with ARM64 as guest and x86-64 as host. The approach itself is not limited to any specific ISA. The design is retargetable, and the generating process is automatic. PerfDBT works with translation units. As long as you feed translation units, it could read, analysis, and reorganize the units automatically. So there is no specific design for a dedicated ISA. It only needs a few engineering effort to support a new ISA.
Okay, thank you. Uh, I don't see any other questions, so we will move on to the next presentation. Thank you again,
Thank you.
Jin. I
Thank
will
you.
welcome Rahul Krishnamurthy he's going to be presenting on the transforming natural language specifications to logical forms for hardware verification. Rahul is a PhD student at Virginia Tech.
I am presenting the paper Transforming Natural Language Specifications to Logical Forms for Hardware Verification. Modern integrated circuits are packed with multiple complex modules and IP blocks to meet the demand for increased functionality and performance. At the same time, due to aggressive time-to-market constraints, the overall design lifecycle has been reduced. As a consequence, complex hardware systems are being developed at a rapid rate, but it is becoming increasingly difficult to verify these designs. This continues to worsen even after spending more than 50% of the time of the project on verification. As shown in this graph, taken from 2012 Wilson Research Group Functional Verification Study, in some projects, even more than 80% of the time is devoted to verification. The verification task that takes most of the efforts is the debugging work. Assertion-based verification is commonly used technique for debugging. In this work, we are automating the assertion-based verification from natural language specification. Automatic generation of assertions from specification documents have the advantage of reduced time to market, early identification of incomplete and inconsistent specifications, and reducing number of design errors. Here is the block diagram of our proposed approach. Input specification passes through chunking module where it is split into smaller phrases. Then, using dependency grammar, the phrases are parsed using transition-based parsing algorithm. Output is a frame if input is a high-level architectural specification. If the input is a low-level assertion that has all required variables, then we can generate system Verilog assertions at the output. The underlying principle of our parsing framework is to view each specification as a collection of semantic fragments. As shown in the specification here, the specification consists of words from W1 to W7, and it consists of two semantic frames, frame 1 and frame 2, that are connected incrementally, and the overall specification is understood. We have created a semantic grammar for hardware verification domain. The semantic grammar describes when and how frames and slots are filled. For example, the implementation of first row in the table is illustrated with a diagram below for the phrase equal to 1. So when the edges for this phrase equal to 1 are created, the relation frame at word equal is filled by value 1 at slot relation object, and this slot relation object is considered as a semantic destination of the value 1. We evaluated our framework on both RTL and architectural level assertions written in English language. We picked 90 RTL specs from AMBA 3XA protocol, and we successfully translated them to system Verilog assertion. One such assertion is a value of X on AW_len is not permitted when AW value is high. Then we tested our framework on high-level specifications, and for this testing we picked ACE and ACE-LAT protocol specification document and took 4 channels of this protocol document. So these 4 channels contain 34 high-level specifications, out of which we translated 22 high-level specification into frames. One such specification is clean invalid, clean shared, and make invalid transactions must not be system shareable. Then we manually wrote specifications of UART and memory controller and successfully translated 80 such specifications. One such specification is when command active occurs, then command precharge should occur before 12,000 clock cycles. In this work, we have developed a semantic frame parser to generate logical forms for hardware specifications written in English language. The output of the tool is in the form of frames and are machine readable. In future work, we would like to enhance the tool with the ability to handle both extra grammatical and ambiguous specifications. Thank you.
Thank you, Rahul. So maybe I want to start off with one question. I don't see anything coming from the audience yet, so I'm going to start off with when I've trying to do natural language processing itself, right? There is some requirements on the way you write as well. Do you have some of these constraints? Meaning, do you have to have some very specific ways in which you need to write the specification for your system to figure it out, or do you have equivalences for certain words and stuff like that?
Yeah, hi. So there is grammar, and we expect user to follow this grammar while writing the sentences. However, at the same time, we have tried to make this grammar very flexible. So make sure that when a user writes a sentence specification, the user need not follow strict order of words in it. So we have added flexibility in writing specifications. So as you said, see, when you write in natural language, you expect to write in some format. So we have tried to make that format very flexible in this work.
Okay. Another thing I also face at our development work sometimes is there is going to be some relationship between what you talk as syntax versus the semantics. How do you kind of handle some of these issues?
Yeah, so the relationship between syntax to semantics is end-to-end. So a single syntactic structure can map to multiple semantics. Also, multiple syntactic structure can map to a single semantics. So to overcome this problem, what we do is we try to, when we parse a sentence and a phrase, we try to consider all possible semantics for that specific phrase, and we narrow down this multiple semantics to a single semantics as we keep on adding more words in the parse tree. So that's how we consider all the possible semantics, and we narrow down to a specific semantics while parsing.
Okay. Rahul, thank you for your presentation. I don't see any other questions. I'm going to move on to the next presentation. The next presentation will be, again, thank you, Rahul, will be it'll be on accelerated verification of parametric protocols with decision trees. And our presenter is Yangjian Li. He is currently an assistant professor. He's an associate professor at State Key Laboratory of Computer Science. And let me get him started.
Our talk is accelerated verification of parametric protocols with decision trees, and this work is cooperated with Typhon Cao, David N. Jensen, John Pang, Xiao Tao Wei.
This video does have some pauses in between. I just noticed it. So give it a couple of seconds.
Our talk is composed of 4 parts. The first one is an introduction of parameterized verification of protocols, and its difficulty, and the limitation of the current research. The second introduces how to learn invariants with decision trees from a datasheet obtained from a reachable state set of a protocol instance. The third one is to apply this learning technique to parameterized verification. Fourth, we introduce our experiments. The last part is on discussions and future work. Parameterized systems exist in many practical areas. For instance, There are cache coherence protocols and distributed memory protocols in the two figures. Difficulty of parameterized verification requires that correctness of any protocol instance with arbitrary size should be checked. Theoretically, this problem is undecidable. Practically, we can't check all protocol instances. Even when the size of a protocol instance is large, model checking the instance can't be completed. Limitations of existing works lies in two parts. Firstly, auxiliary invariants are needed to be found by people. Much manual labor needs to be paid. Secondly, no solid proof is given. Thirdly, we need to understand auxiliary invariants better. In this work, we introduce a decision tree-based learning technique to sum up symbolic formulas to approximate the behaviors of a protocol instance from its reachable state set. We develop a learning paradigm and incorporate it into ParaVerifier framework, which is devoted into a parameterized proof. In the field of machine learning, a decision tree is used for classifying examples. It is a flow chart. Its an internal node is a test on an attribute. Each leaf node represents a class label for a target attribute. Usually we use the decision tree to predict the value of the target attribute basing on the other attributes. For instance, we obtain 11 states from the reachable state set of mutual exclusion protocol instance with size 2. Each state map a state variable like n1 and x to some value. By the classical decision tree algorithm ICCD, we obtain a tree, which is shown in the figure. Notice that a leaf node is returned with a label which is the most common value of the target attribute in the examples. So the classification is based on the most frequent value of the target variable. It under-approximates the data, and predicting the most likely value is not suitable for our verification. We need to accurately predict all possible values of the target variable based on the other variables. So we label a leaf node with a disjunction of formulas which record all possible values for the target variable. This slide has shown how to apply it to partitioning state space. Notice that there are 6 paths in this tree, each of which represents a partition of the state space. This algorithm shows how to make an extended decision tree from a datasheet if target attributes are given. Line 2 deals with the case that decision on the value of target attribute can be made at once because all the samples agree the same value on it. Thus the leaf node is returned with a label target attribute value. Line 4 deals with the case no more attribute can be used to classify target attribute, thus a leaf node with all possible values. Here we need record all the possible values of target attributes instead of the most possible value of target attribute. This change has been made for the use to classify state space completely. Line 6 begin to make branches. Line 6 picks the best attribute to classify samples. In order to make the classification best, we need calculate the entropy of every attribute of the data set. Then partition, split the set into subsets using the attribute for which the resulting entropy after splitting is minimized. Or, equivalently, information gain is maximum. In order to verify that formula in the form of negation f is an invariant of the protocol instance, we call algorithm 2, we construct a decision tree to decide it. We only select the subtable data 0, which contains just columns covering variables of f, and use it to create the decision tree, see in line 3. For each path, we transform this path into a formula, and conjunct it with any symmetry form of f. If it is satisfied, then a counterexample is found. For examples, f1 is an invariant because x equals true and n1 equals c contradicts any path formula in figure 2. But f3 is not because n2 equals t and n1 equals c is contained in the path n2 equals t and x equals false and n1 equals c. We can adopt two optimal approaches to make the datasheet smaller, then learn invariants quickly. One is to take advantage of the symmetry of the reachable state set. Secondly, we can use don't care values to reduce the datasheet further. After adopting the symmetry reduction strategy, the state space reduces from 11 elements to 7 elements. But we need not only check a concrete form, but also its symmetric form. For the Flash protocol in our experiments, the number of reachable states is 107,866,864, while with symmetry reduction and don't care values it is only 857,453. The latter is about 0.8% of the former. So the more complex the protocol is, the more benefit the symmetry reduction gets. How to use the DT deciding procedure? We extend the Parade verifier framework with this new invariant learning approach based on decision trees, see figure 4. Essentially, we use MRFI to get the reachable state set of a protocol instance, and transform the state set into a datasheet. With the algorithm DT decide, we explore the datasheet and construct decision trees as necessary. The trees act as an oracle to check invariant candidates received from InFinder. We have applied our new framework, figure 4, to 6 benchmarks. This table gives a comparison of verification time and memory consumption for the benchmarks between the based oracle and the decision tree based. At first sight, for small protocols, mutual exclusion, messy, the decision tree based oracle is slightly slower than the BDD based oracle, but requires less memory. However, for large examples, the decision tree based oracle performs much better. The last slide is our conclusion. We use decision trees to learn invariants from a datasheet describing the reachable states of a protocol. We apply the learned invariants to accelerate parameterized verification. We integrate the decision tree-based learning technique into Parade verifier and use it as an oracle to learn invariants for parameterized verification. The experiments show that our decision tree-based invariant learning framework can save memory and speed up parameterized verification for large protocols. Thank you for your attention.
Thank you for the presentation. Youngjin, can you unmute yourself? Maybe one question for you. Why do you think the decision trees are doing better than BDDs for large cases, large test cases? I don't know if the author is having problems unmuting. I have ask them Reset, is it something we can do now or we can close the session?
Yeah, so we can close the session. This is the last presentation of the day. So hopefully we'll see you in the morning.
Thank you, everybody. Again, thank you for the authors for presenting the last paper. Thank you.